All right, I think I will start recording here. Get rid of this text. All right, there we are. And we're starting with lesson 5 here. And I think this is going to be the last lesson I do on group theory. So we're still looking at the Jacobson book, Basic Algebra 1. Very good textbook. I think I'm going to stop short of doing the last section, which is on Celo's theorem. So, or the Celo theorems, because there's multiple. Right? So, yeah, Celo's theorems in 1.13 at the end of the group theory section. We're not going to do that. It's something that I can talk about if people want tutoring sessions or something like that. We can definitely go into that. It uses a lot of the stuff from 1.12, which we're going to talk about today, which is the groups acting on a set, group action stuff. But it kind of applies it, so it's a little bit more detailed. The proofs are kind of more in depth, and I won't really be able to give it justice, I think, in a short 40-minute hour segment. So, yeah, I definitely encourage anybody that's interested in it or wants to learn more about group theory to contact me about tutoring. We can set something up. And yeah, I think after this, I'm going to head into some calculus stuff. So I'll do something for maybe like a more broad audience, people in high school, undergraduates, beginning in college, stuff like that. So should be some basic calculus. We can work our way into multivariable calculus as well. But I'll play it by ear, right? So like I said, we're following the book. I'm going to be doing, basically I'm just going to be doing a few exercises today, and then we'll say that group theory is all wrapped up. And like I said, if you have any more questions about group theory or want me to discuss it more, you can talk about it in the Discord. You can contact me personally and ask me, like, Matt, please talk about group theory more, and then I probably will. But yeah, so lesson 5, markers over here, right? Lesson 5, let's just call this group theory exercises. Just took a few exercises that I thought were very illustrative of the stuff in 1.12, talking about group actions. So lesson 5 here, and we'll just call this group theory exercises. Oops. All right, group theory exercises. Hopefully everybody online can see this, or if you're watching this in the future. And again, like I said, we're doing this Jacobson book, Basic Algebra 1. We're looking at page 78. And this is that 1.12 section, like I was just saying. And I chose exercise number 5. Of course, there's many more exercises, but we, of course, won't have enough time to go through all of them. And this question, I've seen this one many times. I think we did this in grad school. Pretty simple to prove. It just says let P be the smallest prime dividing the order of the group for a finite group. So it's important that it's the smallest. It makes the proof easier. Let P be the smallest prime dividing the order of a group. Let's call it G. And then we want to show that any subgroup of H of G of index P is normal. So basically, if you have a subgroup and it's kind of like as large as possible, the index is P and P is the smallest prime dividing the order of the group, then we have to show that subgroup is actually normal. So show that any subgroup H inside of G of index P. Remember I'm not sure if we said this, but this is just common terminology. The index of a subgroup is the size of the group divided by the size of the subgroup. So if your group is size n and the subgroup has size m, then the index is n divided by m. So in this case, when we take the size of the group and we divide it by the size of the subgroup, we're getting p, and p is some prime number. It's the smallest prime divisor of the order of G. So whatever the number is, the number of factors in G, the number of elements in G, p is a factor and it's the smallest prime factor. Okay, so any subgroup of this index is normal. So hopefully the question is clear, right? So subgroup inside of a bigger group, however big the size of H is, it's G is p times as big because the index is p. That's another way of saying it, phrasing it. And now we want to show that necessarily this subgroup is normal. So if we conjugate the subgroup, remember G, H, G inverse, this conjugation action, does it send every element in H to itself, or does it send some elements of H outside of H, right? That's what determines if a subgroup is normal. So basically, we just want to show that G, H, G inverse is just H. And that's the definition of a normal subgroup. So the way we want to tackle this problem is, remember, we're thinking of group actions here. And here, so you want to think of, like, what is the group? Obviously here it's G, or maybe it's something we can derive from G, but in this case it is G. And what is it acting on in a way that we can try to derive some information out of that counting theorem that we were talking about last time. So there's a counting theorem that involves the indexes of the stabilizers of the various representatives of the orbits of the action, right? So here it's important to think about what is the group, what set is it acting on, and then how can we prove the statement that P is normal. And like we said, that just means that if we apply this action to H, this conjugation action, G, H, G inverse, that it should be just keeping within H. Right, so let's try to work this out. Again, you could stop the video if you're watching later and write down the problem or reread the problem. Okay, so P is a prime divisor of the order of the group. It's the smallest prime, and then we want to show that any subgroup of that index, of index P, is normal. Right, so we need to, like I was saying, to approach the problem, you want to think about what is the group, what is it acting on, and what is the action. So here we're going to have the group G. This was our sort of notation for a group action. G is the group, it's acting on a particular set. In this case, it's the set of left cosets of H in G. That's written G mod H. And what is the action? Well, every element G acts by permuting these cosets, and the permutation is given by conjugation by G. Right, so here the action is conjugation. And that means, again, I'll put a little note over here. What is the conjugation action? So G acts on some left coset. Let's say G tilde big H. And the action, so it needs to permute this element, this is one of the cosets, and the action should send it to some other coset. And what coset do I send it to? Well, I just conjugate by g. So I send it to the, I just multiply g tilde h, g inverse. And this should be some other coset, and that's the other left coset. Right. Conjugation. Right. And then the number of left cosets we have is p. So we're going to try to use our counting theorem, right? So the counting theorem said that the number of elements in the set, we could count them using the indexes of the stabilizers of the orbits, right? So the size of the number of cosets was, by assumption for the problem, was p. But our counting theorem also says that we can add up the indices. So we sum over every representative over the orbits, and we sum over the indices in G of the stabilizer of that element, which is a subgroup of G. So this has some index in G, and we sum over all of the representatives, one from each of the orbits. Right, and this is equal to P, which is a prime number. And so here, the special detail here is that we know that all of these indices divide the order of the group, and in particular, if they're non-trivial, they have to be at least size P. But over here, it has to add up to P. So we have a conundrum here. Maybe there's only one element here, and then it would have to be P. But actually, we can show that there's more than one. So in particular, if I conjugate by the identity, then it doesn't change, right? There is no permutation here. You know, identity G tilde H identity is just G tilde H. It doesn't do anything. Therefore, so conjugation by the identity, that gives us one orbit. You know, it doesn't go anywhere. So, right. So when we the identity times H, that left coset, that doesn't go anywhere when I multiply G H G inverse. Actually, I might have messed up on this problem. Let me see. Conjugation. Yeah, left. Yeah, okay. No, this should be right. Actually, yeah. Let me go back to this problem. Yeah, the only thing I'm thinking about is, so you want this to be a left coset here, but it's actually, the way it's written here, we're not really so sure it is a left coset, because this G inverse on the right here somehow needs to be like absorbed into the H, but that's only possible if it is normal, right? But we're trying to prove it's normal. So I think maybe I need to rethink this problem for a second. I wrote this down earlier, but now I'm rethinking this action. Huh. Conjugation. Yeah, I think let me come back to this at the end. Right. Yeah, I'm just not so sure about this action, but the rest of the argument definitely, I remember the rest of the argument follows pretty straightforward from here, which is that if this is P and these indices have to be at least size P if they're not 1, then that basically implies that all of these indices are 1 and that the stabilizers are all of the group for every orbit, right? Meaning that there is only one orbit. It's basically just the identity H, and when you the fact that the stabilizer is equal to G means that when you conjugate by any element of G, you don't leave H. So actually, I think here, yeah. So essentially, the argument just comes down to showing that this stabilizer is always equal to G. And then this index is always 1, and basically you have, you have P of these left cosets, and when you apply the conjugation action, it just doesn't do anything. It's the entire group is the stabilizer, and all of these indices are therefore G divided by G, 1 divided by 1, or sorry, whatever the size of the group is, N divided by N, and it's just a sum of 1 plus 1 plus 1 plus 1, P times, 1 for each of the left cosets. Right. Okay, so basically that argument is all good as long as you prove that this action actually makes sense, that this actually is a group action, right? You have the group G, you have the set of left cosets, and for every left coset and for every element G, you can conjugate by that element G and you get another left coset. And the statement here is that actually that conjugation action doesn't really do anything, that actually the stabilizer is all of G for each orbit, which is just each of the cosets, and this is just a sum of 1 plus 1 plus 1 plus 1 plus 1. Right. So maybe we'll come back to that. That is essentially the whole argument, though. You just have to be careful that, like I said, I was thinking about, does this group action actually make sense, this conjugation action? And to prove that that makes sense, you just have to show that for every left coset, you can define a conjugation of it by any element G, and you get a different left coset. So I'm kind of leaving out a little bit here. We didn't really prove that this action makes sense, but assuming this action did make sense, then you get that automatically all of these stabilizers have to be the full group just by a simple counting argument, and therefore G inverse is just H. It doesn't permute H at all, and that was the definition of normal. So if G inverse is just equal to H, right? You can think of H as the identity left coset. It has like an E here hidden. So E times H, G inverse. Under this action, if it's stabilized under this action, that means it doesn't change anything when I conjugate. So I should just get H back, and that is the definition of normal. If G inverse is equal to H, then H is normal. Okay, so a little bit of hiccup on that problem, but I think it just comes down to proving that this conjugation actually makes sense, conjugation action makes sense, and then apply the counting argument from before. Okay, and then number 6 is a problem about abelian groups, which we haven't really talked too much about, but are very important. Okay, and then so this is number 6, problem number 6. Same section, so it's just the next problem, and we want to show that every group of order p squared, so the square of a prime number, is abelian. And abelian is a property of a group which we didn't really discuss too much, but it just means that if you multiply two elements in the group with the binary operation for the monoid, right, like A times B, you should get the same result as if you do B times A in the other order. So A times B equals B times A. If that's true for every element, then we say the group is abelian. So here, that's basically just what it comes down to. You just want to show that every element commutes, that A times B is always equal to B times A, no matter what the two elements are, A and B. And here it's again a counting argument and a group action, so this time G acts on itself by conjugation. Here we don't have any subgroup or normal subgroup or anything. Here G is just going to act on itself by conjugation, so every element G is going to permute the elements of G by conjugation. So X will get sent to GX G inverse, and that's the action. By conjugation. All right, remember, just conjugation just means, so X is going to get sent to GX G inverse for any element X in the group, and G is coming from the element that is doing the action, right? So X gets permuted by conjugation. And then again, we have this counting argument. So it says the number of elements in the set. So in this particular case, the size of the group, because in this case, we have a group acting on a set, but the set just happens to also be the group. So the size of the set, the size of G, I think they call this the class equation, or maybe that's a related theorem, but for this particular action here, we're going to get that the size of G is equal to the size of the center of the group, which is all the orbits of size 1 under the conjugation action. Those things are in the center, plus the indices of those centralizers of the remaining orbits, the orbits that have size 2 or more. All right, so it's the size of the center. I'll write the center as Z of G. And then we get these indices. We get a sum over the indices of some centralizers. G centralizer of some yi. So this is the index in G of the centralizer of some yi, and we're going to sum over all yi's from the orbits of size, from all the elements with orders, all the elements of that are not in the center. all the elements of the group that the conjugation action, the orbit has at least 2 elements. So they're meaning that they're not in the center. So we have the center elements that are not in the center, but this is basically the same equation that we had written down before. This very useful counting theorem for group actions. Okay, but if we look at this mod p, right? So if we assume that the left-hand side is size p squared, which is what the problem asks, then if we look at the equation mod p and we assume that the center, if we assume that the center only had one element, which was the identity, then these two equations could not be equal to each other or congruent to each other mod p, because the left-hand side is congruent to 0 mod p, since p squared is divisible by p. But if this was 1 plus everything over here is going to be of order at least p or p squared, right? So everything over here is 0 mod p, but we're still stuck with this 1, and that would be a contradiction, because you can't have p squared on the left-hand side, which is mod 0, which is 0 mod p, and then have something that's 1 plus 0 mod p, because 1 is not equal to 0 mod p, or modulo p. Right, so that's a simple argument for why the center cannot be trivial, right? Because if you have 1 plus 0 mod p, it cannot be equal to something that's 0 mod p. So that's just straight immediate contradiction. Therefore, we must conclude that the size of the center of the group either, well, it has to divide the order of the group, right, because it's a subgroup, and therefore the order must either be p or p squared. Those are the only other two things that divide p squared. It's either 1, p, or p squared. We just showed it can't be 1 because it breaks modular arithmetic. So the size of the center must either be size p or p squared. If it's p squared, then we're done, because the center is the whole group in that case, because the whole group has size p squared and the center has size p squared. And in that case, we would be done, because if the center is all of the group, that's essentially equivalent to the definition of abelian. In fact, a group is abelian if and only if its center is equal to the whole group. Right? So again, there's only 3 options for the center. We just gave a quick counting argument for why the center can't have size 1. It could have size p or p squared. In the case that it's p squared, we're already done, because then it's abelian. So really, we just have to derive some sort of contradiction by assuming that the center only has size p and doesn't have size p squared. And that's we're basically just going to assume that it only has size p, and then we're going to actually show that it really does have size p squared, and therefore we'll get a contradiction. Okay. All right, so G acting on itself by conjugation, we're going to write out this class formula, or this the counting formula involving the indices in the case of the set being just G. So we're trying to show it's abelian. Okay, so let's just assume for argument's sake that the center has order p. So the center of the group has size p. Then I don't think we proved this in any of my videos, just because, there's so many things that we could prove that I haven't proved, but there is a theorem that says that if you have a group of index p, if you have a group of order p, so the size of the group is a prime number, then automatically you can show that it's cyclic. So it's generated by a single element, and you can also show that it's actually just isomorphic to z mod pz, or the group of integers mod p under addition. So if the center is p, then we know that the g mod the center also has order p, because p squared divided by p is p. Right? And also you can show that the center is automatically a normal subgroup. So g mod the center is a group itself. It has order p, and therefore these set of left cosets form a group, and that group is also cyclic and isomorphic to z mod pz, so it has a single generator. So that means that g mod the center of G is actually just generated by a single coset, which we'll call little g times the center. Oops. Right, and generated by this coset just means that every element in this group is some power of this element. And remember, every power of this element is just some g to the k times the center as a coset. Right? So if I look at any element in here, so if I look at any left coset, automatically I know it must be equal to g to the k times something in the center here. So, for instance, if I pick, what did I write on here? Yeah, so let's just call it like S or something. Let's just say S is some arbitrary element from the group. Then we know that S times the center as a left coset, well, G times the center actually generates this group. So S times the center must actually be just G to the K times the center for some K. Right, which means actually that the element S is really just equal to G to the K times some element in the center. Right, so essentially you can go through this argument. You can say, okay, the center has index P, therefore the group of left cosets of the center in G is cyclic. It's generated by some left coset G, Z of G. And you can use this to deduce that every element of the group is actually just equal to G to the K Z for some integer K greater than or equal to 0 and some element in the center. And that really helps us prove that it's abelian because these elements G to the K times Z, or if I pick some other like G to the S times some other element T or something, where T is in the center, if we multiply those two elements, then everything sort of commutes because we have these Z and T and they're in the center, so they commute with everything. And then we have this G to the K and maybe G to some other power. And when we multiply those two, we can also commute them because G to the K plus S power is the same as G to the S plus K, right? Multiplying some number of G's first and then some other number of G's is the same as switching the order of the numbers, right? Because if I do like G to the second power times G to the third, well, that's just G to the fifth, which is the same thing as G to the third times G to the second. So the order doesn't matter for cyclic groups. In fact, cyclic groups are automatically abelian. Okay, so essentially the whole argument rests on the fact that every element of the group, therefore, is some G to the K times Z, where Z is from the center and K is some integer. And we just want to show that two such elements that look like this automatically commute with each other. Okay, so basically let's just pick two elements from the group. So the first one is G to the K times something in the center. And the second one is G to some R times T, where T is in the center. So Z and T are in the center. Oops. Center of the group. G is just the generator. Remember the generator of the cyclic group made of the cosets. So G is a fixed element, but Z is just some element from the center, and T is some other element from the center. It's just the element that we deduced has to exist for if x1 and x2 are from the group. And therefore, if we multiply x1 times x2 on the left, well, this is just G to the K times Z times G to the R times T. Right, but Z and T are in the center, so I can change the order of Z and T with any other elements. I can commute it and put it in any, I can change the order of Z and T with any other element, and it doesn't matter. In particular, I can rewrite this as, let's see, I can move the T over here. I can switch the T and the Z. So this is like, actually, let me combine the G's first. So this is G to the K plus R times Z times T. just by moving the z to the other side, moving the g to the r past the z, and then combining the g to the k and the g to the r. So we get g to the k plus r. Of course, k plus r for two integers, when I'm adding two numbers, that's abelian, right? I can change the order, so this is the same thing as g to the r plus k. And I can also change the order of these elements in the center. So t times z. And then I can re-separate this like I was doing, like we combined these before. So now it's just g to the r times t. And I can move g to the k to the other side of t because t is abelian, or t is in the center, I mean. And therefore, finally, I'll write the answer over here, but this is equal to, so g to the r t times g to the k z. And this is exactly x2 times x1. Right, so x1 times x2 equals x2 times x1. These were arbitrary elements because we proved that no matter what the elements from this group were, they had this form. And therefore, because these elements are in the center, you can rearrange everything and you get that x1 times x2 is actually just equal to x2 times x1. And that's what we wanted to prove. Therefore, because it was arbitrary, this is true for every element. And now the group, therefore, is abelian. Right? In the case that the group is abelian, though, then the center can't have order p, right? Because our group had order p squared, and so that's kind of like a direct contradiction there. The center can't have order p if everything commutes, because then the size of the center is p squared, not p. So we get a contradiction. So assuming that the center had order p, we get a contradiction. There were only three options. We showed if the order was 1, that didn't work because of the counting formula. If the order was p, then we proved that actually everything was abelian, so it really wasn't p, contradiction, and therefore there's only one possibility, which is that the center has order p squared, and the entire group is abelian because everything commutes. Everything is in the center. Okay, and then there was one other part of the problem. I'm not really going to prove it, but it just says, prove that the group only has two structures up to isomorphism, and basically you just have to show either it's cyclic and then it's isomorphic to z mod p squared z, or it's not cyclic, in which case you take one generator, which will generate a subgroup of order p, and then take something outside that subgroup, and that will generate everything else. And so basically you have two generators, and you can show that it's isomorphic to z mod p direct product with z mod p, which is not cyclic and has a different structure. But I don't want to waste time on that or go too much into that. So I'm just going to skip to the last problem, number 7. If there's any questions, do not hesitate to stop me. Right, and we may go back to that other problem just to look at that conjugation action a little bit more, because I feel bad about little hand wavy stuff at the beginning. But yeah, I hadn't really, I wrote out the problem and I thought everything made sense, but I hadn't thought of it too deeply, I guess. So we'll just revisit that a little bit. All right, so this is the next problem in Jacobson. Again, this is page 78, or no, sorry. Yeah, page 78, exercise 7. Exercise number 7. So it says let H be a proper subgroup. Of a group G. So proper meaning that it's a subgroup, but it's not the whole group. So there's at least some element in the group that's not in H. And let's assume that G is finite. Finite group. Right, so if it's a finite group, then obviously every subgroup is finite as well. And we want to show that if we take the union over all of the conjugations of H, that we don't get the whole group. So show that the union over G of GH G inverse is not equal to G. All right, so I'll erase this in a second just to make more room, but yeah, we're taking a union indexed over the elements of G, and I'm conjugating H by G each time. So every time I conjugate a subgroup, I get another subgroup, and we're taking the union over all of these subgroups, and we're trying to show that this is not equal to the whole group. Okay. So really this is another counting argument, but it's a little bit of a different type of counting argument. We're not really using that same stabilizer, orbit stabilizer type theorem. This time it's going to be more of like a direct kind of counting argument. So, and right. So let's assume that the index of H in G is K, and K is non-zero, or sorry, K is not equal to 1, or is greater than 1. So H is a proper subgroup. That means if this is equal to K, then it has to be strictly greater than 1. That's what proper means. And we're also going to assume that the size of the group is some multiple of that, because that's always true, right? Whatever the order of H is, or sorry, whatever the index of H is, then the group is some multiple of that. So this is K times N for some N. And N has to be greater than 1 because the group is larger than the subgroup. It's a proper subgroup. Then each time we conjugate by an element of G and we get, every time we conjugate H by an element of little g, then we get a new subgroup. And we're taking the union over all of these subgroups. How large can the union be? Well, it can't be larger than if we assume that it's a disjoint union, even though it's not a disjoint union. But the largest possible thing this union could be would be if we just take the size of each H and each conjugate of H, and we just assume that they're all disjoint, even though we know that they're not, because they all contain the identity. They're all subgroups. So in particular, they have non-trivial intersection. So then basically this union this has to be less than or equal to in size than, well, there's at most n of these subgroups, right? But they intersect, and each one has size k because this conjugation action is a bijection, so it sends a subgroup of a certain size to another subgroup of the same size. So all of these GH inverses are basically subgroups of the same size as H. And since the full group has size k times n, there's at most n of these different subgroups, right? Because there's just not enough elements in G to have more than n. But because they all share the identity, that means that the total number of elements is actually n times k, because each subgroup has k elements, and there's at most n of them. So it's actually n times k, or k times n. But then we counted the identity for each of the subgroups. We basically double counted the identity each time. So we have to subtract off the n times we double counted the identity, and then just add it back once. This is like your inclusion-exclusion formula. We double counted the identity n times, or n n counted it, whatever the n version of double is. We counted the identity n times when we really should have just counted it once. So basically we have to subtract off any of the identities that we counted each time and then just add it back for the one identity that we know is in all of the subgroups. Right, but this is actually strictly less. If n is greater than 1, then this whole thing is actually strictly less than k times n, because if n is bigger than 1, then this whole thing is negative. Right, so kn minus some positive number, strictly less than k times n, but this was the size of the group, and therefore the size of this is strictly smaller than the size of the group, and that means that this can't be equal to the full group. So basically, yeah, we just showed that cannot be equal to g. Because if it was equal to g, then it would have k times n elements, and we just proved that it has strictly less than this number of elements, and therefore it cannot be equal to g. That's what we wanted to prove. Right, so any proper subgroup, if you take the union over all of the, you can call these conjugate subgroups of H, where you take G, H, G inverse, you get a new subgroup. It's a conjugate subgroup. You take the union over all of these, you're always missing something. There's something in the group. Basically, you can't conjugate a single proper subgroup by every element of the group and expect to get everything. There's always going to be something missing, essentially. And this is for finite groups. Okay, so let's go back to that first problem for a second. Try to make that a little bit more clear. Let's see, is there anybody in chat? Just to ask questions, doesn't look like it. Okay, so this is number 5. We're going back to number 5, the first question. And just to remind you, it said we had P was the smallest prime dividing the order of a finite group. Show that any subgroup H of P of index P is normal. And we said that we had G acting on the set of left cosets by conjugation. But now that okay. Okay, so yeah, I wanted to try to explain a little bit more what this action is, and maybe if I wrote down something wrong, we can try to figure that out now. So Gx on the left cosets by conjugation. So really we want to say that G acts on a left coset, or let's say G prime acts on GH by sending it to G prime GH G prime inverse. That's a little confusing. Let's call this G tilde. G tilde inverse. And I guess the claim is that this is also a left coset. So why is this a left coset? How can we rearrange this to show that it's a left coset of H? I guess maybe this action doesn't make sense, possibly, unless H is already normal. Because I think in order to try to commute one of these G's on the other side of H and still remain in H, to be able to do that, I believe is equivalent to being normal. So I think maybe here I'm making a mistake possibly, but I don't know what other action would make sense, because we want to show that it's normal. Show that any subgroup H of G of index P is normal. Yeah, I mean, so if it's index P, I mean, this makes sense that we're talking about left cosets because that's the thing that's prime, which is P. So the number of these is prime. I guess I'm just trying to decide if the conjugation action is the one that makes sense here, or if we should be maybe like the action should be left multiplication perhaps. But then I'm not sure how we get from the left multiplication action to showing that H is normal. So yeah, I believe it is the conjugation action, but that's, maybe the set is wrong, but if we're gonna be using the counting formula and using the fact that it's P is the smallest prime, then I believe that it will have to be, that will have to be the set. So yeah, I guess this just needs to be worked out more, but the details of this action actually being a group action, because if this is not a group action, then of course, you know, we can't use that nice formula that we had, right? So we do have to show that G is permuting these left cosets by conjugation by this action. I mean, this definitely gives you some set. The question is it a left coset of H? And we need it to be a left coset of H in order to apply the theorem, in order to be able to apply this counting argument. So yeah, okay. Yeah, I'll think about this one a little bit more. If anyone has any questions about this problem, or you know, maybe you have a way better solution than me, or can explain this better than me, of course, that would be welcomed. Yeah. I put the Discord link in the chat. If you guys want to join that server, like I said at the beginning, we will have discussions. You guys can ask me any questions. You can always email me. We have our Twitter page, the Discord, and yeah. Please send us any questions, or you know, if you do want tutoring, please do not hesitate. I'm very open. Any times, my schedule is great. So yeah, please contact us for tutoring, any help, really any purposes, math related. And yeah, I think I'm gonna end it here. But this was group actions, and like I said before, we're gonna probably stop groups here. I can go back to any topics and groups in the future if you guys have specific questions, or if you're seeing these videos in the future and you just discover the channel later. But I think I'm going to go into a more popular subject next. So I'll be talking about basic, you know, derivatives, calculus, and possibly after we do calculus, I'll go into some statistics, maybe probability theory, maybe some finance mathematics later. Basically just gonna figure it out as we go. But yeah, this was lesson 5. I'll be here Friday at 4 p.m. and I'm gonna try to keep the schedule Tuesday 4 p.m., Friday 4 p.m., and I'm just gonna put out at least 2 videos a week. So if you're watching this in the future on YouTube, thank you for watching, and I'm gonna end it here.